This is the AWS Developers Podcast. In today's episode, we are at the crossroads of biology, data, and cloud with Phagos. Good morning. Thank you for joining the AWS Developers Podcast. We're available in all your podcast application every Friday, wherever you are on this planet. Please subscribe or leave us feedback, little thumbs up or stars or asterisks, whatever is in your podcast app. This is how also we know the type of subject that you like to listen for future episode. Today, I have the pleasure to not be the only host on the AWS Developer Podcast. Tiffany, you're there. More and more with us. Thank you for joining and being with the listeners of the podcast. And I pronounce with my French accent Phagos at the beginning of at the introduction of the show. It's actually Phagos, it's a French startup at the crossroads of bioinformatics, data, and cloud. That's how I introduce you. But you will be you will certainly explain that much better than I do. I have two guests. We have two guests. Andres Ashboot, you're in bioinformatics and cloud architecture, and Andrea Di Gioacchino, head of data for Phagos. Gentlemen, thank you for being here. Explain us what is Phagos.
Okay, I'm gonna go, and thank you, Sebastian, for inviting us. It's very nice to be here and talk about what we do on an everyday basis. So Phagos is a startup, as you correctly introduced us, at the crossroad between biology and AI and bioinformatics, of course. So what we are trying to do is to help solving the problem of antimicrobial resistance. The problem is that bacteria that infect a lot of organisms in this planet, including humans, are getting resistant to the antibiotics that we use to fight against them. And this is gonna happen, and the World Health Organization flagged this as one of the most important problems for this century. And the problem is that we don't have many alternatives. So at Phagos, we are investigating one of the possibilities, that is using phages or bacteriophages. It's the correct name, phages for short. We call them phages every day, actually, that are the natural predators of bacteria. And we are a company that at the same time works in the lab, in the wet lab, so literally with the pipettes, collecting bacteria and checking phages that are effective against them, but also with bioinformatic tools um, to to understand these organisms from the genetic point of view, and AI to maximize the effect of a limited number of experiments to build a cure made of bacteriophages as soon as possible.
Let me try to rephrase that for a non-biologist person that I am, and I guess our listeners are as well, for IT specialists. You're trying to identify natural organisms that are fighting against bacteria, predators of bacteria, and to use them as a replacement for antibiotics.
Correct.
And these natural organisms exist in the wild. So I guess some of them are known and well-known and documented, and you're trying to find others and transform that into medicine?
Bacteriophages are the equivalent of viruses, but for bacteria. So it works kind of the same. We can engineer viruses, but we can also engineer bacteriophages. That's the reason why I guess in your company you are studying how phages work, how they infect bacteria, and how we can maybe specifically custom phages to target a certain type of bacteria, I guess.
Correct. Indeed, bacteriophages are viruses of bacteria. We tend to say predator because viruses can be misinterpreted. You know, if you start saying engineering viruses, this can sound a bit end of the world like.
No, of course, but yeah, we have to say for our auditors that bacteriophages don't infect humans.
Yep.
So
Correct.
that's where
Yeah,
you
that
can
was
use
my
it.
next question. Is it
Yeah.
dangerous for us? Because if it kills bacteria, what's the impact on the human body?
Mostly from previous experiments, likely none, basically. But it has been observed previously that some phages can have adverse immune reactions, which is very rare. But also another thing that is a possible hazard, but also very rare, is that they can actually um, harbor resistance genes that then later they can be picked up by bacteria. And actually, this is one of the most important things that we do on the bioinformatics side is trying to identify which phages are safe, because that's like the even before whether it's usable or not, it's like the biggest priority that
Mhm.
we don't do more damage than use.
And at what point is it cutting edge? I mean, is there already medicine on the markets that are based on that technology on that approach, or is it really something brand new?
It's very different by countries of the world. I think in like both, especially on the eastern side, in especially Georgia and Russia, there is let's say a bigger experience with them. The In Georgia, we also have the largest institute for phages as well. In the West, in the beginnings of phage therapy, it seemed very promising at first, but then antibiotics came, and at the beginning they were very effective. So phages were quickly disregarded because antibiotics were an easier and more efficient solution. But now they seem to be gone. I mean, not completely gone, of course, but falling out. So phages, it's more like pulling an old tool out of your workbench.
And we are like 5 minutes into this conversation, and I guess many listeners are asking the same question right now. What is the link with cloud, AI, and IT? So I think we understood the value prop, the business that you're trying to build. Why do you need a cloud for that?
As Heinrich was mentioning, phages are a solution that was used in the past. But there are very few cases where this has been successfully used in clinical trials. Actually, the biggest clinical trial that has been done yet failed. Failed because the phages were safe, but not really effective. And the reason is because, at least what we think is the reason, because this is
Mhm.
into research, is that phages need to be considered in the framework of personalized medicine, personalized therapies. And this because they are extremely specific, and differently from antibiotic, you cannot have a drug based on phages that cures a disease. You need to fine tune the phage that you are using in your medicine for the specific bacteria that is infecting the organism. I say the organism also to stress that at Phagos at the moment we work in veterinarian settings. So at the moment we are developing products for animals and not humans. Um,
That's an important point. Thank you.
I think also I can illustrate this with an example of how this process is going without using any kind of cloud or bioinformatics or AI. Because like I think this has not been mentioned before, but phages actually, you Tiffany, you said they have to be specialized, but actually by default they are mostly very specialized to one bacteria, which they
Mhm.
can kill really efficiently. But you don't by default you don't know which bacteria it is, or mostly the question is in the reverse. You have an infection and you don't know which phage it is that can easily kill it. So if you don't do any computational predictions, then and then I have seen this in laboratories, then what you can do is you trial your phage, your bacteria with hundreds of phages, which is a lot of work. And then you select the one that works, which then usually works really well. But essentially, I think what we are trying to do on the entire bioinformatics and data side is to create a shortcut in this and tell the lab members that maybe this is the phage that is going to kill the bacteria, or even if we can just say these are the 10 phages that are the most likely candidates, we have already sped up the process by magnitudes.
Yeah, this is very interesting because, so if I can add a little bit more context, from what I understand, tell me if I'm wrong, but with antibiotics, it's like dropping a huge bomb onto
Exactly.
all of the bacteria, and it kills everything without
Including the good ones.
specificity. Yeah, it kills everything. But also, like, the problem is that bacteria do mutate into, having resistance to those molecules. With phages, it's like if through technology, if you can find the exact key, I would say key to find that specific bacteria that you want to fight, you will just target those bacteria, which is really interesting because if you have an infection on a certain type of bacteria, then the phages will cure. They will target only the bacteria that are responsible for the infection that you want to solve. And this work is just amazing because it allows us to not use antibiotics to specifically target a certain type of bacteria. And as you said, Andres, before computing, it would take a huge amount of work, lab work, to be able to find which phage would kill that specific bacteria. So this is really cool.
What's the type of data that you're ingesting and processing? Where is the data coming from? What are we talking about? What are the volumes?
There are two main sources of data, I would say, and we manage both. One source of data is the output of experiments in our lab, where our biologists measure the effect of one specific phage with one specific bacteria. This measurement is done by measuring how the density of bacteria in a little quantity of nutrient-rich liquid without the phage, and then with the phage. And based on how the amount of bacteria change when you add the phage, you can understand how many phages are killed. How many bacteria are killed by the phage. And this type of data is collected by a machine that can process a lot of this small quantity of liquid in parallel, and goes directly to the data team that creates this. You can imagine this huge table where on the rows there are the bacteria, and on the columns there are the phages, and on each point there is a score, let's say, that says how well the phage can infect and kill the bacteria. And then there is another part of data that are the data regarding the genomes, and I'll leave Andris give details about this because this is more for the bioinfo part.
Yes, well, that is sequencing data, and traditionally we have two types of sequencing. One is nanopore sequencing, which is really good at preserving the continuity of the genome. So it's going to arrive in one piece, which is quite useful for many purposes. And the other one, but it's less accurate. And the other one is short read, where the genome is not necessarily so continuous, but it's very accurate. So with this, we can pinpoint really precise mutations, which, for example, in the receptor binding protein of the phage that it uses to attack the bacteria, it might mean one amino acid might mean infection or no infection. And so this we get from external providers. And then from this, we can assemble the genetic code, which on its own, it's just a large sum of text. But then from this, and this brings us into actually the Nextflow pipelines on AWS Batch, where we process all of these genetic codes in first just mapping where the genes are, then what these genes do, and also trying to predict what is the lifestyle or life cycle of the bacteria, which creates a lot of metadata for each phage and each bacteria, which is then processed by Andrea's team. And here you have to consider that, like, if Andrea just told us about this table where you have the rows and columns of bacteria, we on the bioinformatics team, for each column and each row, produce a lot of metadata which essentially describe the phage or bacteria in a lot of dimensions, in terms of whether it's dangerous to humans, in terms of how many different specificities it can have, and so on.
What is the volume we're talking about for both set of data?
I'd say on our side, it could be terabytes, but not a lot of terabytes.
The raw data size, so the way we use AWS S3, our space allocation in S3 is dominated by genetic data that are, I think, around 10 terabytes. We are talking about um, depending on the species, we work with different species. We have hundreds, several hundreds of strains, so different bacteria for each species, and similar numbers of phages, and the genomes of these things, more or less, with all the data needed to process them, occupy around 10 terabytes.
Here I was only talking about the input data, the intermediate data that is produced. So all of this metadata, which not all of it is used, but most of it can be potentially used. It can be, yes, around 10 terabytes, depending on how often I manage cleaning of legacy files.
You have the genetic data, and then you have the toxicity. I will say, like, the level of toxicity of the phages towards bacteria, and through that you can know you can target which mutation are interesting for which species of bacteria, and at this point, when you identify an interesting string of DNA that could help target a certain type of bacteria. With this, are you trying to also forecast new patterns of DNA to target new species of bacteria?
Yes. So what happens is that I mean, in our imagine, in the ideal case, as Heinrich was explaining, we get um, a piece of infected animal. This is actually, it happens. We get a piece of infected animal, and we know it died because of some, I don't know, like respiratory problem. Let's say, making up things. And then in the lab, we isolate the bacteria, and we see we get the genome of the bacteria, bacterias. I mean, multiple bacteria that are we find in this infected piece of animal, and we have their genomes, right? Thanks to this process of assembling that is done by the bioinformatic teams.
Yeah.
We given that, so this bacteria is new for us, and so it is not in the table, right? And what we are trying to do, and this is more our deep learning effort, is trying to learn
Yes.
from the table and the genomes that we have, how, given a genome of a bacteria and the genome of a phage, if we can predict if the phage is going to kill the bacteria. And this is a project that we are deploying at the moment in the lab, where people can access this. It's an attention-based protein large language model, technically. And this is hosted on SageMaker, by the way, and they can query it through a dashboard. And as soon as they have the genome, they can ask, okay, can please you model scan all the genomes of the phages that are in our database and see if there is a match with this nasty pathogen that we found in the piece of infected animal. And then they will test it in the lab.
This this is amazing. You are using LLMs to read DNA strands,
Of course, yes.
and you can identify patterns in DNA strands with LLMs.
Yes.
This is
yes.
mind blowing. This is mind blowing. I'm amazed. Yeah. Oh, does it happen that this hallucinates patterns or?
It does. We have to put guardrails, meaning that we have to. No, I mean, so, but I
This
mean,
is so cool.
it's also very preliminary. So we have people whose job is dedicated to testing the model, challenging it, and so on. And we cannot. So we cannot let the user do any prediction, because if we go too far from things that the model saw in the training set, then it starts hallucinating, and so it might well say that a phage that has been isolated with a bacteria that is from totally different species will infect something else that is very far. Um, so the model is not the model
Wow.
is not just learning. We also have proof that the model is not just learning the training set and repeating the training set. It's doing more. So it's really
Yeah.
understanding the biology of the part of at least a little bit of the underlying biology. But at the same time, we cannot leave it unguarded. We have to make sure that it's used in a situation where um, its prediction can make sense.
Yeah, it is the first time I hear a use of LLMs this way. This is really, really, really cool.
How do you train that model? Well, so I guess you receive all these data, you need to prepare them, to clean them, and then launch the initial pre-training of the model. What are the type of tools, technology, AWS or others that you're using to build these large language
Okay.
genomic models?
Yeah. So it's a large language model that is trained. So it's actually built in different parts. I cannot give you too many details about it, unfortunately, at the moment. But we are preparing a paper that is gonna get public very soon, um, and where we describe the architecture. But okay, let's say at level of tools, we use. So we had to write the model from scratch, because as you imagine, um, a- as you can imagine, is not a lot of people doing protein large language models. We are not the first. There are very well known models that take proteins as input or genomes as input. Um, there is Evo2, ESM2, ESM3. There are a few models, um, but none of them was really suited to our use case. So we had to, design our own model, and we use of course PyTorch, so the Python ecosystem, and at the level of hardware, it is trained. It has been trained in part on AWS SageMaker and in part on the Euro HPC network. So we sent a proposal for having the possibility of using Leonardo, a supercomputer hosted in Bologna in Italy, and we got this grant. So we had something like 200K GPU hours to
Oh,
train our model as part of this grant in this project that is finishing in the next 2 months. And yes, and then the idea is that the model takes as input both huge public databases uh, that we, of course, have to uh, work on a lot before getting them to a size where there is a level of redundancy that is compatible with this training. Um, and these are basically data from genomes publicly available of bacteria and phages. And then we also use our proprietary data, so the data that we discussed so far, right? So this metrics that contains, let's say, the labels, whether a phage can kill a bacteria, and the genome of the phage and the genome of the bacteria that the bioinformatic team assembled for us. And then eventually, to validate what the model is doing, we also use all the annotations and the metadata that Heinrich was mentioning. For instance, we can see where the model, so what the model pays attention to, and we see, and this one of the, I think, coolest thing we observed so far. We see that indeed the model focuses on tail proteins, so these proteins in the genome of the phage that are known to interact with the bacteria, even though, of course, there is nothing such as an annotation in the training set. So the model learns that it has to look at those to understand if a phage can kill a bacteria or not.
How long does it take to train a model like that from scratch?
We use, at the moment, we use 256 800 GPUs for around 3 days. It's
Wow.
probably not enough in the sense that we are realizing that we are compressing a bit too much the public databases.
Mm.
So to get higher performances, we should let the model see slightly more redundant data, and this means increasing the time that it takes to do a full training. But
Do you apply any type of fine tuning after the initial pre-training?
yes, totally. We use there are some parts of the model that we pre-train with public data, and these get fine-tuned with our data, and some parts are trained directly with our data. So it's quite a complex mix of training from scratch. We also start in parts of the model. The model is quite complicated architecture, and parts of the model they start from a publicly available image, so public available set of weights. So some parts are really trained from scratch. Some parts are we continue the pre-training with a specialized data set, and then some parts are fine-tuned with our proprietary data set.
And how frequently do you need to start
Mm.
again with fresh data? How frequently do you create a net new
Yeah.
model versus continuing the pre-training?
Yeah, so we are exploring this. It is not completely clear. We are seeing that people release. I mean, here there is the growth of our proprietary data set that is growing as the company grows and as we analyze more samples and so on. But also the growth of the public databases, and especially at the level of phages. Bacteriophages are getting more and more popular. So there is really an exponential growth of the number of bacteriophage genomes that are dropped in public databases. And so the idea, I mean, we are considering the idea of retraining from scratch every 3 months. We think that is,
Wow.
yes, that's quite intense at the level of compute power needed. But we think
Yeah,
this,
that's 256
yeah,
GPU for 3 days every 3 months.
yes. And
Yeah.
we think this is the right balance because we observed that the model improves a lot if we don't train it for 6 months. So we think this is not frequent enough. We need to catch these improvements earlier.
That's the training side. I keep an eye on the clock as well. So let's talk about the inference side. Once you have the model deployed, you deploy on SageMaker as well, on Bedrock. And I guess there is some kind of front-end app that you developed as well to allow your user to interact with the models.
So at the inference level, we have a front-end app indeed that the users can use. And inference is hosted by SageMaker as training endpoints, actually. And I wanted to add that we use training endpoints because they offer a lot of flexibility in the way the users actually interact with the models. And this because our models, differently from let's say standard LLMs that interact with humans through text or images, they need to work with genomes that can be quite big, and so we need a different way of for the model to pick these things and work with them and return the answer to the users. So it's a balance that we have to strike between using services that are offered by AWS and let's say do the heavy lifting for us of setting or dealing with all the video drivers, for instance, and communication and so on, with the flexibility that we need because we are working on a, let's say, no standard use case.
I took a note during the preparation about something called NetFlow, but I don't remember what it is.
It's basically a tool that more and more people now in bioinformatics use to orchestrate, because in bioinformatics you have many specialized tools for many organisms and different purposes, and so there's a lot of niches. And whenever you develop a pipeline, let's say for phages or for bacteria, you select out of those niches the tools necessary for you. And Nextflow is really great at taking all of these tools, assembling a pipeline from them, and then setting all of this up on AWS Batch with usually a Fargate head node, and then different EC2s doing the different sub processes with all of these different softwares that annotate different aspects of the phage genome. So maybe to give you an example, when Andrea said that he indeed sees that the model is paying attention to tails, we know this because we have one tool specialized to find genes in phages. So it's really good at finding what are the tail proteins that interact with the bacteria, but also a completely different tool that is in general good at finding subdomains of these proteins. So okay, we have, let's say, this protein, and the model is paying a lot of attention to it. And then we also see that it has mutations in some parts. We can identify whether these mutations are actually in the enzyme that breaks down the cell wall of the bacteria, or just an irrelevant area. So, but Nextflow, I think it has by default good integration within AWS, but there are some puzzle pieces missing, meaning by default you cannot do some stuff on there. And most of my work I mean, I put many hours of work in Fagos into filling these gaps and building like features such as resumability and modularity into the AWS infrastructure, let's say.
Yeah, you have a very specific use case, so it's sometimes probably difficult to find a right fit within the offering of AWS. Talking about that, that's a good segue to my next section. What are the challenges that you had? I'm not talking about the scientific part or the biology part on the IT side, on the cloud side. A specific challenge you had to deploy that infrastructure in the cloud.
From my side, I'd say mainly two things. As I told you previously, for example, cached data for resuming failed Nextflow jobs, they are by default on the person's computer who's using it. And in AWS, I had to set up essentially a database to handle all of these interrupted workflows. But I think maybe a broader answer that also I'm working continuously on actually is to help the bioinformaticians that are working on the pipelines I have described previously, to have their own playground, let's say, as a staging account actually, where they can experiment with modifying the pipelines and seeing the results and making it this as flexible as possible. And here I employed, for example, on the Terraform side, OICD roles for our testing pipelines. So whenever they make a change, they have the option to test all of our pipelines, how they changed, whether it broke anything or not. And at this point, some of this testing is automatized.
Automated. Mm-hmm.
Yes, but there's still like way more details we could go into, in the sense that since these bioinformatics metadata of phages and bacteria, they have a lot of aspects, really like thousands of genes, and then the genes even they have properties like are they involved in the life cycle or not, and how so. So it's very hard to test that if a pipeline changes, then did it change in a good way or a detrimentary way.
It's not only the pipeline, it's the models as well. You must have a way to evaluate the quality of the models. Andrea?
Yes, this is something
Yeah.
we do, of course. And I mean, there are multiple ways, and we are trying to design more and more serious tests that we can do every time we train a new model. Um, so the best test that we can do, that we did a lot, is to train the model, uh, then go in the lab and test it, like test the predictions and check how often the model can predict uh, on new, real, genuinely new bacteria and phages, pairs. But then there are also a lot of other tests that are different, and they, for instance, we can test how sensitive is the model to mutations, uh, how good the model changes, so how fast the model changes mind if we start mutating at random a phage, for instance, and we want the model that is uh, that um, understands that similar phages tend to behave similarly, but at the same time, if the mutation happen in a delicate region, then the model should be able to say that indeed this is bad. And yeah, so there is a lot to do at the level of testing here, and this is really an open problem that we are struggling because I'm, I'm sure whenever there is a new LLM released by one of the big players, you read this table of benchmarks where they challenge each other and so on. Okay, all this doesn't exist for our problem of phages and bacteria. So we are kind of trying to create those benchmarks.
At this point of your research, were you able to either identify or create a new kind of phage that was able to target efficiently a certain type of bacteria?
Creating a new phage is, I think, a completely different story than just selecting the best one against a bacteria. This we've had quite a few examples of where uh, we had a bacteria, let's say, and indeed the lab work of biologists was heavily aided by the model that Andrea has. I mean, Andrea's team, the data team, has developed. But creating a new phage is way more complicated, and also here we really stray into the territory of regulations, especially EU regulations, because that involves because when you consider selecting phages based on the model, it's essentially like breeding dogs, kind of, for hunting. So we breed the best phages. But if you want to create a completely new phage that you did not just find in the wild, then it's GMO. And here I'm also a bit in the dark, but from what we can see, I think in general in the phage field, regulations are likely going to be more enabling in the future inside the EU, and also there's other markets as well. But yes, creating completely new proteins, it's also a biochemical question. So
Mm-hmm. And the other part of the question from Tiffany was, did you already identify an existing one that could be effective to fight against specific bacteria?
yes, for sure, many. I believe, yes. Here, correct me, Andrea, if I'm wrong, but this is, I think, an everyday thing
Yes.
that happens.
But yes, totally. And there are some nice examples where the model that we developed really made a difference. One example is a researcher in the lab who, before this model, was used to whenever she would get a new bacteria, she was doing a little experiment that is quite quick to check a profile of susceptibility against some key phages. And then she would use this profile to find the closest bacteria in our existing collection, and then try to use some phage from our collection that was effective against this so um, that was effective against this known bacteria. And I mean, this approach worked in many occasions, but there was one situation where it was constantly failing, and so she was faced with the problem of having to test everything. So again, for this new bacteria, she would have to test all our phages, but then she used the deep learning model we developed, and I don't remember if it was the highest ranked, so the phage with the highest score that was indeed the most effective, or if not the first, the second. So she could solve it in 2 minutes, which is the time that it takes to scan the full library for one strain.
That's a fascinating discussion, and as I said at the beginning, it's really at the crossroads of biology and IT and artificial intelligence, large language model. Thank you so much, Tiffany Suter, your developer advocate at AWS, Andris Ashboot, you're in bioinformatics and cloud architecture for Figos, and Andrea Di Giacchino. Yes. I hope I pronounce your names correctly. You're the head of data for Figos. Gentlemen, Tiffany, thank you very much. Thank you for having listened to this episode until the end. See you next week for another episode in all good podcast application. But now go build.